Okay, hi there. Welcome to another episode of Science and Technology Q&A for kids and others. And I see we have all kinds of questions here. Let's see. Where should we start? Well, there's a question from Travel here. Why does server farms consume so much power? And what advances are possible with parallel computing to reduce the power consumption or get more computations with the same power? Okay, so why does computation take energy? It's a good question, and actually it doesn't need to. So what happens in a computation? You might be saying there's a piece of my program which says, if this is true, if this thing is a 1 and this thing is a 1, then the result is a 1, otherwise it's a 0. That would be an AND gate. That's a particular thing that exists on a microprocessor. That would be a particular operation that could be performed by a microprocessor. And the question is, why does doing that actually take energy? And in the present day, the reason, well, I'm realizing it's a slightly complicated question to answer. In order to kind of push the electrons through, so these 1s and 0s and so on, they're represented by clumps of electrons. In order to kind of push the electrons to the place you want to be able to do these computations, you have to put energy into pushing these electrons to go to the right place. Now, there's a question of why can't you set it up like you would in like a mechanical system? If you had sort of perfect billiard balls, the billiard balls bounce off each other, and the energy that you put in is kind of regained when the billiard balls go to a different place. And so it is possible to have sort of processes that happen that don't sort of use up energy as they run. And so it was for a long time, it was thought that when you do computation, you necessarily have to use energy. It became clear by about the 1970s that this wasn't the case, that it was possible to do reversible computation. See what happens when you kind of push those electrons through to get results from the computation. You're ending up turning some of the energy that you put into pushing those electrons through into heat. Heat is sort of random motion of atoms. And once energy has been turned into heat, it's hard to get it back again into something more systematic that you can use. So that the traditional way of doing computation involved pushing electrons around, and some of the energy that was used to do that pushing would end up as heat. Actually, part of the reason for that is the following. So imagine that you have imagine you're rolling a ball. You have a ball that's going into some bowl or something. You have a marble that's going into a bowl. The marble the marble goes in, the marble runs down one side, and the marble might just run up the other side. The reason it doesn't run so far up the other side is because of friction, because it's losing energy. If it was the energy that it has, the potential energy it has from being a certain height on one side of the bowl, it will use up that potential energy, turning it into kinetic energy of motion. When it gets to the bottom, then it will be able to turn that kinetic energy of motion back into potential energy and climb up the other side of the bowl. So it will be just, if there was no friction, the marble would just be oscillating back and forth across the different sides of the bowl. But because of friction, the thing will eventually lose energy and come to rest at the bottom of the bowl. What is friction? Friction, in the end, is the conversion of mechanical processes of motion into just heat. It's something where you're taking sort of the motion of the marble, and you're just making things, heating things up, and you're taking that systematic motion of atoms and it's being turned into kind of random motion of atoms that corresponds to heat. Okay, so people thought that if you want to get a definite answer from a computer, when it works out that and computation, for example, they thought you needed something like that idea of friction to get it to come to a definite answer. They thought that if there wasn't something like friction, it would be like, oh, I think the answer is this, I think it's that, I think it's this, I think it's that. It would never come to a definite answer. That to get it to come to a definite answer would need to have something like friction, which would dissipate heat, which means that you put energy in and you don't get anything out from it, you just get heat out from it. That was what people thought. Now, it turns out that isn't true. It turns out that it is possible to make a computer that is completely reversible. And you can do it conceptually by just imagining that your computer is made from a bunch of perfect billiard balls that are perfectly elastic, that just bounce off each other. And with the exact right pattern of billiard balls, you can do whatever computation you want, it turns out. Well, so this idea of reversible computing is theoretically possible. It's never actually been done in practice. Practical computers right now still use the fact that kind of you have to have some sort of friction. You have to dissipate heat to get the thing to come out with a definite answer. And the question is, how fast do you want the thing to come out with a definite answer? Well, the more you can have, the faster you can push the electrons effectively, and the more you can just allow that pushing to turn into heat, the faster you can get an answer. Now, in practice and the design of microprocessors and so on, that turns into questions about capacitance and uses of voltages and sort of details about the way that you're sort of charging up capacitors and letting them uncharge and so on. Let's not get into that. So it's more details of the electrical engineering. But the main point is that the more energy you put in, more or less, the faster you can get things to run, given that there is a certain degree of sort of physical character to these electrical signals and all this kind of thing. So the reason that servers tend to use lots of power is the harder you push them, the faster they'll go. Now, there are details. So, for example, in the detailed design of microprocessors, there are trade-offs about how exactly you'll set up the wires, whether you'll have these sort of crosstalk between wires when that happens, whether you'll have certain features of the way that the characteristics of the individual components work and so on. And by tweaking the engineering, you can end up with using less power because things sort of just go more smoothly in terms of the way that the underlying physics of the device is set up. And sometimes by letting the thing run slower, you can use less power. But so typical server farms have this trade-off between how fast do they go, how much power do they use, exactly what design does the thing have. And sometimes when people have really redesigned microprocessors from the ground up, it's been possible to design them to work with lower power. So, for example, in the whole sort of story between Intel and ARM, two different major microprocessor design companies, there's sort of been issues. For example, there was for a while the issue that sort of ARM had in a sense simpler designs, not as sophisticated as Intel's designs. But those designs were sort of created from the ground up, and it was possible to make lower power versions of them, which is why ARM processors, one of the reasons ARM processors became popular in cell phones, because that was a place where power was at a premium, whereas in servers, it's like the thing is connected to the electrical grid, and you can just put power through it and get computation done. In terms of whether things like parallel processing will help with this sort of the power that's used in servers, probably not so much, because when you're computing, you're computing. You're doing it in parallel, you're doing it sequentially, it doesn't really make much difference. I know for my computers, they have many cores in them, and if you start running a program that is making use of many parallel cores. So normally when you run a program, in the simplest way of setting up a program, the program has a series of instructions in it, and those instructions get executed in series. And so on your computer, there's just one, the computer is just saying, I'm at this point in the program. Okay, I'm going to move the program counter to another point in the program, then another point. It's sequential. But in modern computers, there are often multiple cores, multiple different pieces of microprocessor that can separately run programs. And so it's pretty common to want different programs to run in different cores. And for example, your operating system on your computer will be running the different programs you're running in lots of different cores on your computer. But sometimes you have a single program where you want to divide up the work into multiple cores. Let's say, for example, you're going to process a whole collection of photographs, and you're going to, I don't know, you're going to turn every cat in every photograph green or something, and you want to go through and you want to use some machine learning algorithm to turn every cat in every photograph green, and you've got 1 million photographs. How are you going to do it? Well, you can have a sequential program that just opens each photograph, does its thing, and turns the cat green, saves the file again, goes on to the next one, goes on to the next one. But let's say your computer has, I don't know, 20 cores or 8 cores or 4 cores. It makes more sense to have those separate cores, each separately go out and deal with their group of photographs and do all those things in parallel. But when you do that, and when each core is doing some sort of computation intensive thing, you'll often hear your computer start to make more of a noise. What's actually happening? What's happening is the CPU is all those different pieces of the CPU, all those different cores are starting to be used, and the computer is using more power, and it has a fan typically that is, or many computers have fans that are kind of blowing air across the top of the CPU chips to keep them cool, because they're using more power, and so they're going to heat up. And what happens is, usually there's a certain operating temperature, range of temperatures for microprocessors. It's determined by the fact that if you make the electrons in the microprocessor too hot, if you make the microprocessor, if you make the semiconductor that the microprocessor is made out of too hot, the electrons will start kind of moving around in the material, even in ways that you sort of didn't tell them to move around by putting voltages on and so on. So there's usually a maximum temperature at which a semiconductor device can operate. And so you have to, if you're starting to put more power into this device, you have to be pulling power out by blowing air across it and having sort of heat exchange happen and so on. And so that's why when you're making your computer do more work, the fan will start up as it's trying to blow air across that microprocessor to keep it cool, so that it doesn't go to a temperature that's too high, that where it switches off. I discovered once, I remember, when was it? I think it was when I first had an iPad a very, very long time ago, when iPads first came out. I left the iPad on the dash in a car, and it was a sunny day. And this iPad, because it had effectively a black screen when it was switched off, was just absorbing sunlight like crazy, and it got really hot. And I was kind of impressed that when I tried to switch the thing on, it came up with this warning thing saying, this iPad is too hot. It will damage itself if it switches itself on. Let it cool down before it can be operated. And that was a microprocessor that had gotten outside of its normal operating temperature. So that's why these things have to be cooled in elaborate ways. And so if you go into in a typical, if you go into a server room, server farm, for example, they're often called server farms. I'm not sure whether that's a good comment on the way that animals are kept in some kinds of farms, but because they're just rows of servers that are just doing computations and so on. And a typical server room we set up in so-called hot aisles and cold aisles. So you have all these rows of servers, and they're all stacked up. They're usually the pizza box form factor is a pretty common one, where the actual computer is the shape of a pizza box, basically, and it's fairly thin. Sometimes they're called blades. Where the circuit boards for the computer just lie horizontally, and you're stacking them all up to make this big server, big configuration of server room. And usually what will happen is there's a side of it that's cold, where it's being cooled by the air conditioning in the server room, and then there's a back of it that's hot, where it'll just be blowing out waste heat from the operation of the server. And that's sort of a typical setup. And it's often the case that the amount of computation that can be done, the number of servers you can put in a server room, is limited by the rate at which you can get heat out of the server room. And so sometimes people do crazy things, like they try and have server rooms sort of embedded in glaciers, or there was a trend at one point of having underwater servers that were kind of dissipating heat to an ocean. There's a more amusing version of that, which is if you have, for example, high altitude drones that, for example, are providing things like cell phone service. You can do computation in a high altitude drone where it's getting power from sunlight and so on. And because it's really cold at 60,000 feet or wherever the drone is operating, you don't have to have the kind of cooling that you need to have in a server room. The drone can just, as it's flying through the air and it has a server on it, the server will just be cooled by the low temperature of the air at the altitude that the thing is flying at. And so you can kind of optimize things in terms of cooling. But in terms of what will the future be in terms of power consumption of computers, my impression is that the engineering progressively gets better, and it's progressively possible to sort of remove all those little stray things that use more power than they should. It will take some new technologies, I suspect, to dramatically reduce the amount of power that's consumed. And certainly some of the technologies that people use for what they imagine to be quantum computers, even if they're not really quantum computers operating really according to the laws of quantum mechanics, some of those technologies, particularly ones with optical, with light and so on, instead of electrons, instead of electricity, some of those will likely lead to things that are computations that take a lot less power. So that's a comment about that. Let's see. There are questions here. Boy. Okay, there's a question from Erin here. Have you ever had a situation where UUIDs collided and caused some sort of issue? Well, that makes me talk about what UUIDs are. I've sometimes said when the UUIDs collide, the universe will end. I say that somewhat facetiously, but let me explain what UUIDs are and how this works. So UUID stands for Universally Unique Identifier. So let's say that you have a whole network of computers, and you're going to have a file that's created on one of those computers, and you want to make sure that that file is named in a completely unique way. So even though you didn't check with any of the other computers, oh, do you have a file named this? Do you have a file named that? You want to make sure that the name you come up with for that file is going to be universally unique, that no other computer will come up with that same name. You might also do this if you were, for example, if you were generating addresses for little devices, and you were going to have 1 trillion devices in the world, and you want each of them to have a unique address. One way you can guarantee that they all have unique addresses is to have a registry where you're listing all those addresses, and you check for every new device you add, is that address I'm trying to add in the registry or not? If it's in the registry, I can't use it. If it isn't in the registry, I can use it. But the point of a UUID is to avoid doing that, to use the fact that if you have a long enough number and you pick it randomly, the chances are that that will never be picked at any other time. So in other words, if you were to say, I've got 1,000 possible IDs that I can use. Well, by the time you've got maybe about 500 different things where you're picking the IDs, the chances are you'll have a collision. The chances are 2 things will both randomly get picked as ID number 205 or something.
And then whatever system you had that relied on the fact that no two different things ever have the same ID will just will fail. So the idea of a UUID is that you have something where it's a long enough, randomly enough picked number that the chances are it will never be picked. The same two-name number will never be picked ever again in the sort of history of the world. And typical UUIDs are these days, what is it, 256 bits, I guess. So they're usually written out in hexadecimal. So hexadecimal is base 16. We usually use base 10. And so in hexadecimal, they're numbers 0 through 9. And then there's an A for 10, B for 11, et cetera, up to F. So those are the digits of hexadecimal. And usually UUIDs are numbers that are written out in hexadecimal. That's the most common way they're presented. But they're fundamentally just numbers. But they're numbers between 0 and 2 to the power 256 minus 1. And those numbers, that's the typical choice of UUIDs, that number is big enough that it's, for example, larger than the number of atoms in the universe. So if you were to use a UUID to label every atom in the universe, there's a good chance that if you picked that label at random, that every atom would get a different label. So that sort of seems enough that the UUIDs aren't going to collide. The question is, to make sure that UUIDs don't collide, you have to pick them at random. If you say every Tuesday, I'm going to pick UUIDs of this form, well, that's bad news, because then the chances are you'll end up picking two identical UUIDs. It's the same kind of problem as if you're trying to pick a password, a key for a cryptography system. You want to pick it sufficiently randomly that same key won't ever be picked again, or that people won't be able to guess what you picked. So there's sort of a challenge of how do you pick the UUID randomly enough that the same thing won't get picked again. It's not that difficult in practice to do that. So I've never seen a case where UUIDs collided. So many systems in the world today depend on UUIDs not colliding that I have no idea what would happen. It's a good kind of doomsday scenario to figure out what happens if the UUIDs collide. I don't know. I think a lot of things where the identity of a thing is determined by UUIDs would get very confused. And people where they think they're two different users of a computer system, it would be like, oops, the UUIDs have collided. They're actually the same user. And that would get very confusing. And things where only one user is supposed to have permission to see something, well, actually another user with a colliding UUID would get permission to see it, and so on. A lot of things would go crazy in the world. So we have to sort of hope that that UUIDs won't collide. And we can know that so long as they're picked randomly enough, they won't collide. I might tell a piece of history that some of you may know, some of you may not know, about kind of things people assume about computer systems and what goes wrong with them. This is about the Y2K problem. And this is supposed to be a Q&A for kids and others. So the kids may not know about the Y2K problem. The others may know about the Y2K problem. What happened is, heading for the year 2000, there was a big sort of panic about the way that computers stored dates, because computers had typically stored year, month, day, and the way they'd stored as a date. And the month they store as, 08 or something for August, the day they store as, 15 for the 15th of the month. And it's like programmers had thought, well, let's just store the year as 2 digits. It's all good. That was a decision that was made in the 1960s. And it's like, let's store the year 1998 as 98. Let's store, et cetera, et cetera, et cetera. Use just 2 digits. Well, the problem is that a lot of programs said, is this date after that date? And so they would say, we compare the dates. So first we compare the years. Is this year after this year? Okay, well, the year 1998 stored as 98 is correctly identified as being after 75, which means the year 1975. But if you're storing things only with 2 digits, by the time you get to the year 2000, that doesn't work anymore. The year 2000 is after the year 1999, but 00, the number 00, is before the number 99. So the sorting of dates would be got wrong. So people really started to panic a few years before the Y2K, year 2000 moment,
of, oh my gosh, all the computer systems in the world are going to fail. And so a bunch of companies that sold sort of systems that deal with particular transactions and databases and things, they were like, this is the most fantastic opportunity we've ever had. We can finally get people to upgrade these systems. They've had the same system for 20 years. They've never been upgrading it. It's going to fail. Let's not patch the thing. Let's just have the thing fail and say the only way you get to have a system that works when Y2K happens is to have a new system. So there's a huge amount of activity in sort of patching up computer systems so that they didn't fail at the moment where Y2K happened. And people really thought that there might be a possibility, the air traffic control system would fail, the nuclear power stations would fail, the electrical grid would fail, that at that moment where Y2K happened, the world would end. It's kind of like the Mayan calendar, which has this feature that it eventually wraps around, and people sort of wonder if the world is going to end where the calendar wraps around. People were really wondering what was going to happen at that moment when at the beginning of the year 2000, when two-digit dates would have failed in that way. And I remember we had done a lot of stuff at our company to try and be ready for Y2K. Some of it was probably overdone, actually, because there was such a sort of generated panic about Y2K. And I remember at the moment where Y2K happened, I was like, let me send a piece of mail to all the people at the company, Happy New Millennium type thing, and let's get that right at the moment of Y2K, and let's see if anything actually fails. Well, it didn't. Actually, interestingly enough, there's another Y2K-like problem in the year 2038 that's coming, because in Unix, common operating system and common sort of foundational operating system for many computers, there is it's often the way that Unix stores times is as seconds after after January 1st, 1970. And it turns out that the number of seconds after January 1st, 1970, by the year 2038, will be more than the number of bits that you can store in a 32-bit word. And so that if for systems that have 32-bit, that use 32-bit numbers, there'll be a sort of Y2K-like problem in the year 2038. I don't think it's going to be very serious because everybody will have moved to 64-bit systems. And I think the sun will no longer be shining when 64-bit systems run out of seconds. So it's so we don't have to be too concerned about that. All right. There's a question here about, I think coming back to servers and things like that, from Reem. Why does Bitcoin use so much power? Let's see. Well, all right. Basic point. What is Bitcoin? Bitcoin is a cryptocurrency that is based on the idea of blockchain. What is blockchain? Blockchain is a way of recording transactions. It's a way of having this chain of recordings of transactions where it's set up so nobody can fake it. It's set up so that you store, this person paid this person such and such a number of Bitcoin. This person paid this person. And if somebody says, I've got this Bitcoin, I can pay you, somebody can go back, the system can go back and automatically check, is it really true that you still have that Bitcoin, or did you already spend it? And so there's this ledger that goes all the way back to when Bitcoin was first deployed in what, 1998? Am I getting my years wrong? Around that time, is that right? Has it been that long? No. Maybe I'm off by 10 years. Maybe it's 2008. In any case, when yeah, I think it's I'm off by 10 years there. So when Bitcoin was first deployed, the first transactions were recorded on the Bitcoin blockchain, and transactions have been being recorded on that blockchain ever since. And the way it works is there are maybe 10,000, maybe 20,000 copies of the Bitcoin blockchain and on different people's computers all over the world. And all those copies are consistent. And so when somebody says, do you really have the right to give me this Bitcoin? You can go check any of those copies of the blockchain, and you can make sure that, yes, that Bitcoin hasn't been spent. It's good. You can go ahead and give it to me, type thing. Okay, so the question then is, how do you decide when a transaction happens, how do you decide that that was a valid transaction, that it really happened, and that you should add it to the ledger of transactions, to this blockchain of possible transactions? And there are a variety of different schemes, but the one that was picked for Bitcoin was a thing called proof of work. And sort of the idea is people can, let's see, how deep do I want to go into this? People, the notion is you have to decide who is going to add the next block to the blockchain. For Bitcoin, a block is being added about every 10 minutes these days. And what's happening is within each block, there'll be this whole big list of maybe, I don't know, 1,000 transactions that happened that are being recorded on the blockchain for all time. And the question is, in order to put that block onto the blockchain, you have to make certain cryptographic things connect with the previous parts of the blockchain. There has to be sort of a valid way that you add that block to the blockchain. But the question is, who gets to add that block? And you want to be the person adding that block, because every transaction that's in that block being added to the blockchain comes with a certain commission. And if you get to add that block, you get to take all those commissions. You get to be paid in Bitcoin all of those commissions. And so you want to be the person who adds the next block to the Bitcoin, to the blockchain. Question is, how is it decided between these 10, 20,000 different places where the blockchain is stored, these different, who's going to add the next block? Okay, so in order to add a block, the rules of Bitcoin are such that you have to solve a particular, essentially, computational puzzle. And the puzzle is basically, there's all of the data that corresponds to a sort of a hash code. Hash codes are, you take some collection of data and you kind of mash it up and you get a number out of it. And so you might have a huge amount of data and you mash up that data, you just get this number that's a 100-digit number, let's say. And hash codes are useful because the chances are two different kinds of data that you mashed up will end up with different 100-digit numbers. So if you want to find out whether these two things are the same, you just compare their hash codes and that will tell you. Well, sort of an abuse of the idea of hash codes is what happens in Bitcoin, because what's happening there is one's asking, can you find a way to take all the data that exists on the blockchain plus a little extra piece, it's called the nonce, and to arrange the nonce so that when you take all the data on the blockchain plus the nonce, that the hash of all of that is a number of exactly a certain form that starts with a bunch of zeros. Okay, so the problem of blockchain is that the way you decide who gets to add the next block is who's the first person who picks the nonce to get the hash that has the right number of zeros at the beginning. I forget how many it is now, maybe 14 zeros I think it's got to now. And the difficulty of finding that hash is being made more difficult every few years as you're required to find a hash which has even more zeros at the beginning. So what's being done, Bitcoin mining is the process of trying to find those nonces effectively that will generate a hash that has the right number of zeros. Now, and to do that, the only way people know to do that is you just try a lot of hashes. You just try a lot of nonces and you see what the hashes are. And suddenly, if you try enough of them, chances are you'll say, aha, I'm the winner. I've got the one that starts with a bunch of zeros. And so that process of Bitcoin mining, that's what it involves. And the sort of concept is that these are so-called cryptographic hashes, and they have the property that there's really no way you can find out whether the hash will have the form you want except by just running the hash and seeing what happens. This is very related to this idea of computational irreducibility that I developed back in the 1980s. And I think it's very likely that the originator of Bitcoin knew about that idea. And that was sort of the origin of sort of this notion that you can have to do irreducible computational work to achieve something. But so that the idea is that so what's happening is people have made all sorts of special purpose computers and things, and they count the number of gigahashes, the number of billions of hashes per second that those computers can do to try to find the nonce, to find to add the next block. And so people
that's so what's happening, the energy that's being used in mining Bitcoin is just running all these hashes to try to see whether you can get the one that is going to allow you to validly add a block to the blockchain. So this is an incredible waste of electricity. It's when I invented computational irreducibility, I never imagined, I could never imagine anything like this as a sort of application of computational irreducibility. Why does it make any sense? It makes sense because you want something that is sort of hard to make. You don't want something that doesn't take any commitment to make. You don't want something where everybody can just say, I got the block, I got the block, I got the block. You have to have some way of deciding. It's kind of like you imagine people digging up gold. Somebody is the person who gets to find that gold deposit and go to all the effort of mining it, and that's the person who gets that piece of gold. And it's the same kind of idea here in Bitcoin. And I think people say that the total amount of electricity used in Bitcoin mining is comparable to the electrical output of Denmark, and it's predicted in a couple of years it's going to be comparable to the electrical output of Italy. I don't know if this is all correct, but lots of electricity is being used in Bitcoin mining. A question you might ask is, could Bitcoin mining be actually solving a useful problem instead of doing this kind of computational puzzle of solving hashes? I have wondered about this. I've never figured out how to make it something where it's solving a useful problem, because you kind of have to know, in a sense, you have to know the form of the answer in order to validate the fact that you got a correct proof of work, so to speak. So it's hard to have something where it's doing something useful where it doesn't know the answer. Although as I'm thinking about it, telling you about this, I'm thinking about whether there's a way to get something where there is an answer and it gets to that answer, but there is an intermediate step that was necessary to get to that answer, and the intermediate step is useful. The answer is known, but the intermediate step is useful. The other issue with computations that are useful is it may be more difficult to know for certain just how difficult the computation is expected to be. Although the truth is that with cryptographic hashing, it's a question of, did you guess the right thing by good luck or not? There are other approaches used in other blockchains. The most popular is there are many different ways to decide who gets to add the next block. Sort of another one that's becoming popular is proof of stake, where you're basically showing that you own a bunch of that cryptocurrency and you get to sort of vote on what the next block is. That's a different way. In fact, Ethereum is just transitioning to something close to that. Maybe it's just happening right now. Ethereum 2.0, I think, uses that kind of method rather than the just burn computer time to solve these computational problems. Let's see, there's a question here from Slayer, very different kind of question. What is the correlation between sleep and weight loss? Boy, I don't really know. I think a lot of that information is so deeply anecdotal. I mean, it's always, we don't really completely know what the function of sleep is. I've always assumed that sleep is necessary to clear kind of junk out of the brain, much as when muscles get tired because they build up lactic acid from sort of repeated nerve, the repeating of that of the operation of the nerve on the muscle, just as one builds up sort of the waste product of lactic acid in muscles, so one must be building up some kind of waste product in the brain as a result of having a sort of waking day. And I think people say adenosine is one of the possible things that is produced as a waste product from the sort of electrical activity of neurons in the brain. And then sleep is sort of a time to clean that out. And sleep, because of the way biology tends to work, once it has a capability, it's going to pile a lot of other pieces of functionality on top of that capability. So it's like, okay, given that you've got the animal asleep, let's have it do this, let's have it do that, let's have it have a time when its digestion is doing this, or when it's something else is doing that. And I think so sleep ends up getting used for many purposes. Even if its primary purpose might be sort of cleaning out gunk from the brain, it's getting used for lots of different things. And some of those things probably have to do with some of the kinds of things that relate to one's metabolism and so on. Certainly one knows that, temperature goes down at night, heart rate goes down at night. I'm not sure how all of those things play together. And I think a general finding is people need a certain amount of sleep. And if you don't get it, bad things happen. Things like your immune system stops working as well. You're more likely to, catch a virus because your immune system is not as aggressively attacking it. All sorts of different things happen. You don't think as clearly because something is kind of gunking up your brain, perhaps. But so there are different things that happen when you don't have enough sleep, and I think it's one of the things of modern times. I don't know what's happened to people's sleep during this pandemic. I kind of think it might have gotten better. That there's people in many periods of life tend to have a sort of chronic lack of sleep, where they're like, well, I've got lots of things to do, and then I got to get up very early in the morning. And certainly school systems have had a terrible habit of getting kids to get up super early in the morning, even though the way that we are all synchronized, we have this kind of circadian rhythm that tends to synchronize when it is that we think we should sleep, and it's sort of synchronized to the sun, and it also tends to be aligned relative to the sun. And I think people generally believe that particularly kids are actually quite unsuitable as teenagers and things, at least, to be getting up super early in the morning. And it's kind of a crazy thing that, for example, schools often start very early in the morning. And I think that's been something, there's been some pressure against that, but it's something which sort of the societal structure of things is such that, well, it's really good to get the kids off to school because then the parents can go into work or whatever. And so that's how that develops, but it's probably not the optimal thing in terms of cognitive performance of the kids and so on. But so I think, so I don't know the answer to the relation to weight loss. So Erin is pointing out that the number of atoms in the universe is actually larger than the size of a 256-bit UUID. As I was saying that, I was remembering that I think I mentioned this in this little book I wrote called Elementary Introduction to Wolfram Language. I think I discussed this question of just how big is the typical UUID, and I'm remembering this point. You're absolutely right that it wouldn't quite make it to label all the atoms in the universe. The question of how we know how many atoms there are in the universe, we know how big the universe is. We know there let's see, there are about there are about 100 billion galaxies in our universe. Each one has about 100 billion stars in it. Each star has about 10 to the 57 atoms in it. And so we know from that roughly how many atoms there are in the universe. It's about 10 to the 80th atoms in the universe. That's 10 times 10 times 10 times 10, 80 times. So it's if we count it out, a trillion is 10 to the 12. So if we counted it out, let's see, can I do the math here? It's a trillion, 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 trillion atoms in the universe, which is quite a few, but and more, as you are correctly pointing out, than you fit in a 256-bit UUID. So at the point, which is not going to happen in our universe with the evolution of our universe, at the point in the very, very, very distant future of our universe, that when the time that our universe, the 14 billion years that our universe existed so far, when that time looks like something infinitesimal, when the universe has evolved, many, many, many orders of magnitude more than that time, then maybe we will be at a point where the UUIDs that we have today will have sort of more serious problems, so to speak. Of course, it's not clear. There are many other weird things that can happen in the universe before we reach that point. Gosh, okay, all sorts of interesting questions here. There's one from Mahmood: how to convert black and white video to color. So this is something people have been doing in recent times. You've got a black and white movie that was made in the early 1900s, and it's like, let's colorize this. And the traditional way to do that
is people with paintbrushes, effectively. You take every single frame and you go and you kind of change the color of the black and white areas in every single frame. That's the traditional way to do it. And by using human judgment, you say, this this cat was yellow type thing, and let's just decide in this cartoon that was made in 1925 or something, let's just decide this coat was red, and then we color all those frames in the right way. Okay, the thing that's become possible recently is more automated colorization. And the way that works is as follows. It's using machine learning and using neural networks. And essentially, here's the idea. Imagine that you could show a computer examples of zillions and zillions of different pictures. Maybe you could show 100 million pictures. And each of those pictures has things that have certain shapes and certain colors. You have a tree. It's got green leaves on it. The tree is a certain shape and the leaves are green. You have the sky. It's up there and it's sort of plain and it tends to be blue. You have different kinds of things and they tend to be certain colors. So essentially what one wants to do is to say, given the shape, we know 100 million examples. We can look at the shapes in those examples and we can say, what color did a thing of that shape happen to be in that image? And so then if we can learn from those examples, we can say, given this movie frame that has a picture of this, this, and this in it, we can reasonably guess, based on the examples from those 100 million images, we can reasonably guess the sky up there is blue, the grass down there is green, et cetera, et cetera, et cetera. And so the idea of colorization, automated colorization, is that idea that you learn from all these examples and then you implement it in the particular case that you're showing. Now, how does that learning work and so on? That works using these things called neural nets, which were kind of invented as a idealization of what's happening in our brains. And essentially what goes on there is that, well, it's a fairly complicated story altogether, but roughly you've got a program that has a lot of different variables in it, millions and millions of variables. And what's happening is you're saying you want to train this program to follow certain examples. So you might show it a picture, it says, that's an elephant. You say, no, it's not, it's a cat. And what it's doing then is it's setting those different numbers inside the program to be such that, okay, it said it was an elephant, but actually it should have been a cat. So let's tweak those numbers to make it say it's a cat in this particular case. Show another picture. It says, that's a car. And you say, no, it's an elephant. You tweak the things a little bit more to say, okay, make that be an elephant as well. And you keep doing this tweaking and you do it billions and billions of times. And after enough time, you can have ended up tweaking it to the point where it'll more or less get things right. And it'll more or less say, yes, that really is a cat in that picture. And so you can do the same thing with colorization. You're progressively training using existing images, and you're getting it to the point where it correctly says the grass is green, the sky is blue, etc. And that's how this automated colorization mechanism works. And you can find in Wolfram language, for example, we have some colorization neural nets that will do this kind of automated colorization, and it works fairly well. It's not perfect, but it works fairly well. It certainly can bring some black and white pictures somewhat to life. There's a question from Heather here. How much sleep do I get a night? I'm one of these people who knows a disgusting amount of information about myself. And I have all that data. The answer is about 7 hours usually. And I usually make sure that I kind of budget for 8 and expect to get 7. I think over time, I have probably needed a tiny bit less sleep. It's kind of a feature of the horribly aging brain. But I kind of think that in the effort to preserve it as long as possible, getting enough sleep is an important thing. And I recommend it to everybody. And it's kind of like one of these things where you can say, well, let me get less sleep. I think only, oh gosh, I'm trying to remember how many all-nighters have I pulled in my life. I can remember one of them when I was a teenager. Have I pulled other ones? I've certainly
I've had things where changing time zones and flying around the world, I've had sort of somewhat strange sleep schedules. But I think I've been convinced that all-nighters don't make a lot of sense, partly because what I find is if I'm really tired, I don't think very well, and I can't do the things I want to do. And it's much better to just sleep, and then I'm actually alert and I can figure stuff out and things happen fairly quickly. And I can be like tired and I'm like, I don't really know, and can't figure anything out. So in worst case, I'll take a one of the things that's been an advantage of getting older is it gotten progressively easier for me to like take a nap for 15 minutes and have that work. I think when I was much younger, I used to have much more trouble, falling asleep. And I made an active effort when I was a teenager, actually, to, lie on one's back, close one's eyes, just fall asleep. And I finally got to the point where, yes, I can really do that. It's sort of a reflex to do that. And that has the terrible feature that, in all sorts of strange situations where, I'm at the dentist's office and I'm, I have to say, I'm sorry, don't mind me if I fall asleep, because when I'm in that kind of position, I sort of have this reflex of falling asleep. But it's been a useful thing to learn and something that helps me. Okay, let's take a look here. Let's see. Question here from Aaron asks, what kind of car do I drive? And what's the difference in technology that fascinates me versus technology that I just see as utilitarian? Oh, interesting question. I mean, I've never been a big car enthusiast. I haven't driven a car very much at all in the past year, but I have, what do I have? I have some kind of BMW X5, I think is the designation. I think that's right. The fact that I don't even know exactly what kind of car I have is kind of a sign of a lack of profound interest. I got this car. I think my wife basically picked this car out for me, and I've generally not been, and it sort of has, the technology is okay, and doesn't have anything that's sort of horribly in your face, not kind of, badly designed technology. I had a previous car that was a nice car to drive, but it had just really challenged technology. I have to say, when I got this car, this is just a personal silly story, but when was it? Two, 3 years ago, I'd realized that I had a previous car for 10 years and I still didn't know how to do certain things with that car. It had all kinds of controls, and it's like, I don't really know how you get this to work and that to work and so on. And in fact, some things just didn't make sense. And, I tried to figure out, how do you get it to, have its GPS work without having the radio on or something? And it just like, you just can't do that. So this time when I got a car, I decided I would do a thing that was sort of look, am I going to really read the manual? Am I not going to read the manual? And I was like, okay, just get the car dealer to spend, an hour and show me how the car works. And I have to say, they were a little bit surprised. It seemed at being asked that, and it turned out it wasn't as educational as I'd hoped, but it did allow me to know, oh yeah, you press that button, there's this little door that opens here. And it's like, I would never have found that. I could have driven this car for a decade and I would never have known that. So thanks for telling me that. It was a useful piece of education. But I would say that it's sort of a big trade-off between what technology do you really sort of put effort into understanding, what technology you just use for the sake of using it. I tend to always try and get the kind of most leading edge gadgets and devices and so on, unless they just don't work very well. And there's sort of always this trade-off of, do you have things that have been well polished but don't do as much, or do you have things that do all kinds of cool stuff but have all kinds of rough edges? And it's always a trade-off for me, which of those things I will end up being dealing with. And like, for example, the thing I wear on
my wrist is that measures heart rate and motion and so on, is not actually the very best and latest technology, because the best and latest technology doesn't bundle in things like getting text messages sent there, and I don't want to be wearing two different things. I mean, there was a period of time when I was wearing a thing on one wrist, a thing on another wrist, and a thing on my ankle. And that was like, oh, this is too crazy. I'm not going to do this. So that's the trade-off there for me. But I think it's always. I also tend to be somebody who, when I'm using some technological device and I find some kind of bug with it, I make a point of actually reporting that bug to the company that makes the device, because I know from being on the other side of that story, people will say, oh, I've been using Wolfram language for years, and oh, there's this really annoying thing that happens. And you say, really? And maybe it's a bug, but maybe they just didn't understand how to do something. But even if it's a bug, it's like, I wish you'd reported that 10 years ago. We would have fixed it 9 years ago then. But nobody ever reported that, because nobody ever had, a gamepad together with a Zulu keyboard together with a this, together with a that. And this just never came up before. But sorry, you've been the person who is the one person who has that particular combination. And so you see this. All right, let's see. There's a question here from Slayer asking, can I explain the differences between DC and AC? All right, he says, famous last words, a fairly straightforward sort of piece of physics and engineering. So what's that about? It's about when you're going to have, when you see, this is what always happens. The things that I think are like super straightforward to explain, there ends up being a little bump before one gets to them. But okay, so this is about electrical power, and it's about how one delivers electric power to things. So for example, when you have a power outlet in a typical place in a typical country, you're plugging you plug that plug into the wall, you're getting a certain electric current from the electric grid that you can use to power your devices, your computer, whatever else. Also, when your computer is connected, you have this adapter that goes plugged into the wall, then you plug the other end into your computer. The wire that's connected to your computer is also, there's electric current going through that wire. But the electric current that goes to your computer is a little different than the electric current that comes out of the wall, so to speak. And the difference is that what's coming out of the wall usually is AC or alternating current. What's going into your computer is usually DC or direct current. Okay, what's the difference between these? The issue is there is a voltage. The voltage is kind of what pushes electrons through wires. When you have a voltage, it's like there's a high electric potential, a low electric potential. It's like you're making a ramp and you're forcing, and the electrons go down that ramp. So when you're having a plus voltage on one side, a minus voltage on the other side, that's defining a potential difference, which is kind of a thing that pushes electrons from one side to the other. And because of a vagary of the way things have worked out, you'll actually push electrons from the minus side to the plus side, because electrons are negatively charged things. But that's sort of a detail. You're basically pushing, voltage is pushing electrons through wires. So direct current is you're always pushing the same way. You just push the electrons through the wire. And batteries, for example, produce direct current. They produce a voltage that's always pushing in the same direction. So another thing is alternating current. And what's happening with alternating current is you're pushing the electrons one way for a short time, then you reverse and you push the electrons the other way. You push them the two different ways. And for many purposes, it's perfectly sufficient to just have electrons be pushed. For example, if you're trying to heat something up, you just want electrons to get pushed into something. The fact that they get pulled out later, pushed in, pulled out, doesn't matter. They still, by this sort of motion of the electrons, effectively, you're still heating things up. Doesn't matter that you have alternating current. For other purposes, it can matter. For example, if you're running a computer, it can matter that you always are pushing the electrons the same way. You need direct current. So why is alternating current? So in actual electrical supply in the US, for example, it's at 60 hertz, which means 60 times a second, you're reversing the direction of the voltage. And it's a sine wave, so it just wiggles up and down 60 times a second. In some countries like England, it's 50 hertz. Some other places, it's usually 50 or 60 hertz is the typical frequency of the electrical supply. And usually it's pretty precise, actually. There's a considerable effort is often made to arrange the frequency to be pretty precise. It used to be the case that electric clocks would actually use the electrical frequency as the way of deciding of measuring time. That's no longer done. It's just oscillations of quartz crystals, or alternatively just data that comes from the internet that sets time. But back in the day, that it used to use the frequency of electrical supply. Okay, why do people use alternating current? Well, the main reason is that when you're going to you're going to send electricity over a long distance, you lose less power in heat with alternating current than you do in direct current. And so if you're going to have, and actually it's even more than that, the higher the voltage, the less you dissipate heat. And so when you're sort of taking electricity long distances, when you're, for example, you have a power station that's a hydroelectric power station that's sitting right there at the position of a waterfall, then you're generating power at the hydroelectric dam, but you want to use power at the city that's 500 miles away. So you have to have wires that take the electricity from the hydroelectric dam to the city, and usually the main wires are operating at high voltage because that's the way you lose the least power in transmitting. So usually, I think 20,000 volts is common, 100,000 volts is also common as the voltage that you're sending, and that's always alternating current because that loses less power. Now, back in the day, there was a big sort of competition when electrical devices in the electric grid were first getting developed. Thomas Edison and, was it George Westinghouse? I think that's right. Westinghouse versus Edison, big kind of competition of who would end up being which system would end up being the winning system. Am I remembering this history correctly? And I think Edison was not on the right side of, I'm trying to remember who was on which side of that story. And I remember all kinds of crazy, terrible things about demonstrations of electrocuting poor animals with direct current and things, and showing that alternating current didn't work as well, but it was sort of a fake experiment, and all kinds of skullduggery, but having to do with which got picked. But in the end, for the main electrical supply, partly for this reason of power dissipation, and for other detailed reasons of which technology got developed first and so on, alternating current was the thing that got used for large-scale electrical supply. Alternating current has to be converted to direct current for things like computers, and that's what that little box that is between the electric supply and the computer, that little box is the thing that does the conversion. And I have to tell a little story against myself there, that many years ago, there's a physicist who claimed to have invented some zero flux transformer that would transform alternating current to electric current. And somebody I knew was really wanted to know, is this going to work? Should I invest in this invention? And I'm like, I don't really know, but this physicist is a person who does particle physics. I don't know why they would know anything about electric transformers and so on. It's a very different design from any transformer design that's existed up to this point. And I kind of, it's like, I don't really know. I don't think it's going to work. And that would be my assumption. Well, many years go by, and then I realized that actually that physicist, to their great credit, pushed this idea forward, and it became the standard idea that's used in essentially all, has been used until recently. There's one new idea sort of come on the horizon that's been used in sort of essentially all adapters that go from
from mains AC mains supply to the DC power that's used in computers. And one of the things that's actually clever about this particular form of adapter is it used to be the case that if you wanted to go from 110 volts, which is in the US what the peak voltage, actually it's the is that the peak or the RMS? It's the voltage that characterizes this alternating current. If you want to go from the 110 volts, that is the mains power, to the whatever it is, 6 volts or 9 volts that you need for your computer, that you have to pick. You have one transformer for 110 volts. If you go to England where it's 220 volts or 240 volts, you need a different transformer. But this methodology for making a transformer allows you to have one transformer that doesn't care what the input voltage is. It can do the transformation of the electric current. So that's kind of the story of and now this question of whether you can transmit, whether there are ways to transmit direct current over long distances. One of the things that happens is if you could make an electrical wire that has much lower resistivity, where the electrons, usually when electrons go through a wire, they keep on bumping into atoms effectively in the wire, and they keep on being sort of not allowed to keep flowing without running into any interference, so to speak. And in superconductors, they're special materials which at sufficiently low temperatures, the electrons can just flow through them without effectively running into any obstructions at all. So they have zero resistivity, zero resistance. So the electrons just go through without running into anything, without dissipating any heat. So the problem with superconductors is they only exist, the only ones we know about are ones that exist at low temperatures. So you have to have liquid nitrogen or even liquid helium to cool down this material to the point where superconductivity happens. It's long been thought one day there will be a room temperature superconductor at which sort of just in the everyday world, it'll be possible to have a superconducting wire. If that happens, the electrical grid will be transformed. I'm sure DC will be what's used most of the time. And the electrical wires we see, which are right now made of copper usually, will transform to being made of high temperature superconductor, at which point the sort of the economies of AC versus DC will change. Okay, well, I should probably there's one question here I have to maybe address from Motu. If I walk into a very powerful solenoid, will the magnetic fields affect my nervous system or have any other physical effect on me? That is a much debated question. So clearly in us humans, so okay, magnetic field, if you're in a very big magnetic field, for example, MRI machines usually use very big magnetic fields. So if you're getting an MRI done and you're in the MRI machine, there's usually a pretty big magnetic field that's going through you because that's necessary for the way that an MRI machine works. That's the M in magnetic resonance imaging. It's all about the magnetic field. So the question is, if you have a big magnetic field going through you, does it have an effect on you? If you have a magnetic field that's rapidly changing, is it different from having a magnetic field that's just a static magnetic field that you would get from just a big magnet? The answer is nobody really knows. There isn't probably the most obvious things. Nothing terribly obvious happens. Nothing terribly obvious goes wrong with us humans in high magnetic fields. But it's quite likely that there are actually things happening. So it used to be said when I used to be involved in particle physics, I used to go visit particle physics experiments. And this was in days when they were a little bit less fancy than they are today, when they only cost a few $1 million rather than tens of millions of dollars. But they would often have these huge magnets. And physicists would say, you know what, if I stand inside that magnet when it's on, I get a funny taste in my mouth. And that's not a completely crazy thing, because the way that taste works, it involves electrochemistry, and it can involve electrical kind of magnetic. There could be an interaction of a magnetic field with some of that electrochemistry. I have to say that I have had the belief, which I don't know if it's correct, that when I pick up a strong magnet, my fingers start tingling.
And my children at various times have tried doing experiments on me to see if this is really true. And the results of the experiments are let's say they're not definitive. But there's sort of a question: if you pick up a very heavy magnet and you have that magnetic field, particularly if you wiggle the magnet around, can you, when you have a changing magnetic field from wiggling the magnet around, you can induce electrical currents. And the question is, can you induce electrical currents in your nerves that will cause you to like feel tingling in your fingers just from wiggling that magnet around? I would say that in me, the jury is still out on whether that really happens or not. Now, if you ask, do magnetic fields have an effect on anything in humans? We're not sure about humans. In pigeons, it's pretty likely magnetic fields have an effect. It's pretty likely that in the brains of pigeons, there is something that detects the magnetic field of the Earth, and that's used by pigeons as their sort of GPS-like device to know how they navigate, to be able to be a homing pigeon and navigate back to where you were coming from and so on. And so it's believed that there are devices in a pigeon's brain that are sensitive to magnetic fields and which presumably would be completely scrambled by a big magnetic field. I mean, presumably if we humans had that kind of thing, it's kind of like, how does the pigeon feel about its view of the world? You put the pigeon in a big magnetic field and, the pigeon is going to go, look around, and you can have a big debate about whether this pigeon is having a good time or a bad time, whether it's having the time of its life getting this big magnetic field. It's like, I'm having a great bath of magnetic field, this is wonderful, or whether it's having a terrible, this is horrible, I've got this terrible sensation in my brain. It's hard to know because it's tough to know what pigeons are thinking. But whether we humans, and so the mechanism by which magnetic fields can affect neurons in a pigeon's brain is not well understood. It's thought to be something quite quantum mechanical. It's thought to be something where it has to do with electron spins. It has to do with the best current theory, I think, is that certain chemical processes, certain processes in biomolecules and the molecules that exist in proteins and things like that there are places in proteins where the direction of an electron spin can affect the rate of certain chemical reactions. And so what happens is when there's a magnetic field that causes the direction of the electron spin to turn, and usually electron spin doesn't have any effect on the rate of a chemical reaction. But the claim is in some particular cases, for some particular proteins and things, that it can have an effect, and that's how you can have you can have a sensor that is sensitive to magnetic field. And the fact is that one of the things that happens is proteins tend to pick up all kinds of, like a protein will it's made of amino acids, always made of the same kind of stuff, but it can have these cages that can enclose particular kinds of atoms, like hemoglobin in our blood has a cage that is specially set up to enclose an iron atom. And that's how we get the iron that transports oxygen in our blood, is the hemoglobin protein has this cage where as soon as you get any reasonable amount of iron, the iron will get stuck in this cage in the hemoglobin, and then it can be used to transport oxygen. And there are similar theories about various atoms getting stuck in cages, and that's related to the way this magnetic field sensing works. All right, I think it is time for me to go to something different here. So thanks for lots of interesting questions, and I look forward to addressing more of them next week. And so come back again next week. And I think next Wednesday, I will also be doing a live stream, and we're doing those in a 2-week cycle. And so next Wednesday is about business and innovation. And then this time next week, I'll be doing another science and technology Q&A. So thanks for joining us. And